All right, let's go ahead and get started real quick before we begin. So you all may have noticed this or not, I'm not sure, but I have posted a homework for this topic, and it's mostly T-beams, but there's one doubly reinforced beam that we'll get to probably today, if not Monday. Here's that. Here's that. Mr. Yukonik, you would appreciate one of the problems as it is a box beam. But so, what's that? Wait, what?
Fifth graders are building a roller coaster. Like not anyway. Real. A real one. Would you like to build a roller coaster? No. So why don't you go ahead and talk about the structural analysis of the roller coaster? Like predicting compensation.
Oh my goodness, come on. They're fifth graders. All right, let's move on past that. So I do have a friend of mine that I went to grad school with, and she now works for Disney designing roller coasters. I am quite envious of her.
How does that, I'm sure they're, like, the engineering behind it is kind of the same, but at the same time, I'm sure it's not.
Well, I mean, the geometry is fairly much more complicated, or fairly complicated. I mean, the tributary area calcs and things like that are way different. Well, that and parabolas and all of that. So, there is that component of it. Plus, you'll find a lot of, like, drag forces and lateral forces because, I mean, you have a, heavy moving component on there. So, yeah. And plus, I mean, it's one of those things where, structural engineers in practice love designing nice straight rectangular boxes, and then you go design a roller coaster and it's nothing like that. So now, if you've ever been to, how many, this is going to be a random question, but how many of you have ever been to Toronto? Okay, have you ever been inside the CN Tower?
No, but I've seen it.
You've seen it, okay. So inside the CN Tower, which is the tallest structure in the city, there's a quote-unquote glass floor. So a floor you're not going to walk on. So it's not made of glass. It's like some composite polymer or something, and it's probably designed for like 1,000 PSF or something ridiculous like that. But I mean, I'm not going to lie. The first time that I walked on it, I was like, whoa. But then, within 10 minutes, I'm, sort of like jumping up and down. What?
There was like a thing like that in China. It was on the side of the mountain and it collapsed and killed people.
All right. We'll All right.
How would you design something like that on a Disney building?
Carefully.
Bolts are well.
Group B. Group B bolts. There you go. Okay, let me get back to the lecture notes. All right. What's that?
This works so well.
Yeah, I know. This is going to be awesome. Okay, so I'm going to try and stretch out the recap just so I don't have to use paint use paint again. No, I do want to kind of recap where we were off last time. So the big issue with T-beams is whether or not you're dealing with a rectangular T-beam or a true T-beam. Okay? Now, one nice thing about T-beam design is your geometry is usually known. You usually know your flange thickness because it's essentially a slab, so you've got that pretty much pegged out. And you've got your geometry of your beam figured out from a number of things. You might have designed the rectangular portion as if it was just a rectangular beam, and then you're going through these motions to see if you can cut down on the amount of reinforcement. That's a possibility. Another possibility is you've already got the beam size for things like deflections, things like what comes next after moments, which is shear, which is what we're going to talk about probably sometime next week. So, your geometry is usually known. But like I said, the big issue is whether or not you're dealing with the case on the top or the case on the bottom. If you're dealing with the case up top, it's pretty simple. I mean, it's a rectangular beam like what we've done before. So solve for your row required and move on. If it's a true T-beam, it's a little different. Okay, so how do we determine whether or not it's a true T-beam or a rectangular T-beam? Based on the row that we compute, we back calculate A. Back calculate A, if that depth is greater than the flange thickness, then our stress block goes into the web and we're dealing with a true T-beam. So if we've got that case, we use that simplification that we did before where we split it up into a flange couple and a web couple, and we solve accordingly. Now, the way that we do that is we say, well, based on this geometry, I can calculate a phi mn for the flange couple and a phi mn for the web couple. And for each of those phi mn's, there's going to be a corresponding area that we compute. Now, the way that we do that is we say, all right, because the geometry of this first one, this flange steel couple, is known, we can actually just directly solve for how much steel we need there. It's pretty straightforward. We look at our two couple expressions, and we say, all right, if we've got to have steel for each of those, we say, well, the flange steel couple, I just set C equals T and solve for the area, and I get a little bit of area for this flange steel couple directly solved for. So that's the first one. The second one, I say, well, I know how much moment the whole thing has to resist, so I subtract that off, solve for the nominal moment capacity of the web steel couple, and say, well, based on that, back calculate your steel. So here's your process. Step one, we compute the factored moments on the beam. Maybe they're given to us, what have you. We assume a phi value of 0.9 and compute our Mn required. Now for step three, we start off at the beginning and say, let's assume it's a rectangular beam. If it's a rectangular beam, we can compute rho required and then back calculate A. If that A is less than the flange thickness, then we know that that assumption is valid and it is a rectangular T-beam. If not, then that assumption was incorrect and we have a true T-beam. Now if it's rectangular, just calculate the area of steel, pick a pattern, move on. If not, then our calculations become a little bit more involved. So we say, all right, if it's a true T-beam, we can directly solve for how much steel we need for the flange. So the area of steel for the flange is as follows. Then based on that area of steel, compute the nominal moment capacity of the flange. That's all we can get out of it. If we know this moment capacity, we know how much we have to resist, compute the moment capacity of the web steel couple, get the amount of steel we need for that using rho BD. So we'll choose a pattern that's based on the flange steel and the web steel, and that's how we'll design our section. And this is a note I put, this is something we really haven't talked about a lot, but if you need to use multiple layers for a problem like this, use it, It's just something worth mentioning. All right. Last thing, just analyze the section. Everybody good? Help me out. Normally I would be able to open the notebook, but today I can't. So did we do this one? We finished this one, didn't we? Okay. So we got this one to do. Now I think we actually did a little bit of math on it, but we're just going to have to start over. Oh, okay. Well, let me summarize that a little bit. Okay. All right. And now the fun begins. Okay, so if I What's that? Give it some time. All right. So we had MU is 920 foot kips. And that's been given, right? Okay. Step 2, we've got compute I could write like a poster for a Renaissance fair or something. We had, what was it, 122. Oh, that's right. Thank you. They're vacuuming upstairs.
Betty, stop.
Did that yesterday.
I think it's today. The one in there from the other classroom looks right when you're.
So this is where we left off last time, right? Okay. So based on these values, we found that A was greater than or equal to the flange thickness, which is 3 inches for this problem. And therefore, we are dealing with a true T-beam. Should I put like oh goodness. So if we're dealing with a true T-beam, we go to step 8. Okay? Now step 8, we need to deal with the flange steel couple. In other words, we're dealing with a section where we know that the depth of our stress block is going to be in the web. So because of that, what I'm going to do is compute how much steel is needed for the flange couple, and then compute its moment capacity, and then based off that go and back calculate how much we need for the web. So I'm going to compute the required area of steel for the flange directly. And it's a pretty plug and chug count. It's just 0.85 FC prime B minus BW HF over Fy. Now how do I do that? I say that, you know, C equals T. I'm saying that the tensile force is Fy times the area of the steel, and then the compressive force is 0.85 FC prime times the area of the flange. Solve for how much steel you need, which is just divide the whole thing by Fy. So that is, what's the, is it 3K? It's 3 KSI for this problem. And then, what's the flange width? You all have the problem in front of you, right? There we go. Minus times what's the flange thickness? That gives you that. Okay? So that's part of the steel that we need. Okay? We'll figure out the rest here in a little bit. Everybody got this? Now, what I am going to do right now is I'm going to say, all right, therefore, the nominal moment capacity of the flange couple is, and I put that as a sub, that's going to bug me. D minus HF over 2, right? It's the force. It doesn't matter if I use 0.85 FC prime B minus BW HF or just this because C equals T. So it's this force times the moment arm, the depth, minus half the flange thickness. Okay? So that is, what's this? This is the moment capacity of the flange couple, that component of it. We're doing this part because it's a true T-beam. Yes. All right, so that is plug and chug, and that will give you now, if I just literally take these numbers and plug them into the calculator, what are my units that come out? I mean, what's in this expression? Inch kips. And divide by 12. Foot kips. All right. Does everybody understand so far? Everybody good? Okay, so what I have done is computed, based on my beam geometry, this is about how much moment capacity I can get out of that flange steel couple. Now that's not enough. The beam is subjected to what? The beam is subjected to 920 foot kips. So I need more capacity. Okay? How do I get that capacity? I need to determine how much capacity I need from the web. Okay? So therefore, step 9 compute MNW. Maybe I'll use orange. To sort of split my steps up. Oh, goodness. That's bugging me. Okay, does that make sense? All right. So let's see. Compute the required moment capacity in the web. Now, how do I do that? Well, MU is 920 foot kips, and MN for the flange is 559.41 foot kips. So therefore, MN for the web is MU minus MNF. But the problem is that you got to make sure you're doing apples to apples. So this has to be factored. And technically, if you factored your moment, that would lead to a phi value right here. So if I divide that out, that's how I get this. All right? Does that make sense? Everybody okay with that? So I've got 920 foot kips minus my phi, and I'm still in assumption mode for phi, so we'll say 0.9. 559.41 foot kips. is 462.82 foot kips, or 5553.8 inch kips. Now, while you all are writing that down, there's a couple things I want to just say right off the bat. I'd argue that one of the big hurdles that you all dealt with on the first celebration were units, okay? And the problem was not that you didn't understand the units. I think you all got that. But what you would do is this, is you would do that, like, instead of actually writing it out, you'd say something like, well, we'll just say 920 minus 0.9 times 559.41 over 0.9, and you actually didn't write it out, okay? Now, I know it's a test, and I know there's a time issue, but that stuff matters, and that's the stuff that messed a lot of people up on their exam. So, you know, I'm sure that some of you are probably looking at this and going, well, couldn't you have just multiplied this by 12 and then, you know, gotten inch kips in the end and used that value instead of this? Doesn't matter what you do as long as your units are consistent, okay? So you can argue that there's probably different or better ways to do this, and that's fine, but notice how every calculation I'm doing, inches squared, KSI, inches and inches. So I know what my answer is in the end. Does that make sense? Whatever you do, it doesn't matter. Just make sure that you're consistent. All right. All right. Okay, has everybody got this? Okay. Do a little orange line. Okay, so step 10. Now that I've got how much nominal moment capacity I need for the web, I can now compute how much steel I need for the web. And I can treat that like it's a rectangular beam where the cross-section's known, because it is. So I'll compute the area of steel for the web as follows. I'll start off by computing rho. And keep in mind, because we're dealing with the web steel couple, we're only caring about that little width, so we use B sub W, not B. So plug and chug. B sub W is 15 inches. And this is 24 squared. MNW is 53. I'm curious what you all get. Keep in mind units. This is something I want to point out. Look outside the bracket. You have KSI over KSI. It cancels. Okay? Look inside. Okay, the numerator is inch kips here. What about the denominator? KSI times inches, that would be kips per inch. Then inches squared, that would be inch kips. So inch kips over inch kips cancels. So everything inside the bracket is unitless. Everything outside the bracket is unitless. Reinforcement ratios have no units. So it's all about making sure that the numbers going in make sense. Okay. I'm going to make you all do this one. Like, okay, yeah. Yeah. Something about like that? Okay. All right, so that's our reinforcement ratio. Therefore, the area of steel for the web is rho. And maybe I should do this. Maybe I should put rho. I should delete that. Maybe I should put rho W required. Just to sort of emphasize what we're looking at is the web. It is the reinforcement ratio for the web times the area of the web, BW times D. So that comes out to be about 4.526 inches squared. Make sense? Everybody good? Okay. So, for your trial design, and keep in mind it's trial because we've still got to make that check of our fee. Ultimately, the one assumption we haven't dealt with is fee. Here's what our trial design is going to look like. Obviously, it's a T-beam. Okay. Let's see. We've got okay. And this is BW is 15 inches. Everybody okay with this so far, right? Okay, now, you all help me out with this because you all have the numbers in front of you. We calculated an area of steel for the flange and an area of steel for the web. Now, the area of steel for the web, I'm looking right at it, it's 4.526. What about for the flange? What was that? Okay? So we need to pick a reinforcement pattern that has an area of steel of 9.499 inches squared. Does that make sense? And I propose to you that the easiest way to do that, or the most economical way to do that, ten number nines, okay? Maybe I'll make that a little bigger. Okay? Now, if you're curious about this, I'm going to put a note here on the side. Okay? to get 10 number 9s to work, the web is only 15 inches wide. So I propose that you need to do a layer of 5 bars and a layer of 5 bars. If you look at the bottom of that beam design chart, for 5 number 9s, beam in is 14.3 inches. Okay? So you can get by with doing that and it will work. Does that make sense? So there's nothing wrong with using 2 layers of steel. And maybe one thing I should do is indicate that D distance is to the centroid, the center of that group of steel. Everybody okay with this? The last thing that you need to do is there's that one assumption you need to verify. You need to analyze your trial section. Okay? So MU for this beam was the factored load, and it was what, like 920 foot kips? If you go through and do the phi-m-in calcs, you're going to get a phi-m-in of 953, or wait, no, 935, sorry, 935. And since I'll go ahead and throw it in here, just for posterity's sake, AS min. So based on this, what do you think? This isn't too bad, is it? Now, Mr. Yukonik has a wonderful ability of asking about topics like a week in advance. So he actually asked about this a little while ago, and we're going to address it. And that's what comes next. Doubly reinforced beams. How do you deal with steel if it's in compression? Okay. So first off, does everybody have all this? Okay. I think we're not going to have time to actually do any examples. We're just going to talk about it. So, but in the meantime, I am going to give you all a doubly reinforced beam handout. Now you do have a doubly reinforced beam on your homework, but it's just an analysis beam or an analysis consideration. To be perfectly honest, I'm actually not too concerned with your ability to design a doubly reinforced beam. That's not really what I'm after, and it's usually not what you're going to be interested in when you go to design a beam. Like if you're needing to use double amount of reinforcement to meet moment capacity, you either have some stringent architectural requirements or something's wrong with what you did initially. So it's not really as big of a concern from a design standpoint for me. But there are some benefits from an analysis standpoint to at least considering the fact that you have double amount of reinforcement. Now, I don't know that I have a good picture in this initial slide, so maybe I'll go to my shear lecture notes. What I mean by doubly reinforced beams is something like this, and this is just a rough conceptual drawing to give you kind of an idea, but if you look at the rebar inside of a reinforced concrete beam, we tend to call it a rebar cage. Usually you have a bunch of steel at the bottom. That's your tensile reinforcement. These stirrups, these bent pieces of rebar going like this, we're going to look at designing those later. That's to resist shear. But to tie everything together, you tend to put a couple bars on top anyways to make the cage sort of solid and whole and what have you. So that's what we're going to look at is, what is the contribution of that reinforcement. Now, there are benefits to considering the fact that you do have rebar up there more often than not. Compression steel is usually there to support the stirrups anyways. So, I mean, if you can squeak out a little bit extra capacity by just considering it, there's no problem there. Also, and this isn't going to really make a lot of sense right now, but it will later when we look at beam deflections. When you add compression steel into a beam, you actually get a little bit of benefit from a deflection standpoint. One of the things about concrete that makes it a little more of a difficult material to assess than something like steel is that concrete's material properties tend to change over time. Okay, that concrete on day one does not behave the same as concrete 10 years from now. And anybody who's had any experience with that will be able to testify to that. Concrete experiences some material-related phenomena that change its properties over time. One of those properties is a phenomenon called creep. Has anybody ever heard of the term creep? Okay, so if you have creep, it actually sort of flies in the face of everything that you learned in mechanics of deformable bodies, but it happens, okay? When you take mechanics of deformable bodies, you think, okay, load and displacements are always proportional. In other words, if I have a bar and I yank on it, it will displace. If I yank on it more, it will displace more. But to make that bar get longer, I have to yank on it. Creep is where the bar gets longer, but the load doesn't change at all. Okay, and that doesn't really make a lot of sense, but think about it like this. I have here a piece of chewing gum, and imagine if I hung this piece of chewing gum up and I attached a weight to it and then just left the room, came back an hour later. You think this would be longer? It would just kind of stretch over time, wouldn't it? It's a material phenomenon associated with chewing gum, okay? Concrete's the same way. Maybe not as drastic or dramatic as something like that, but in the end, over time, concrete will deform under constant load, okay? That's called creep, okay? There's an opposite effect that actually happens in steel. In steel, under a constant length, the force can dissipate. You can get reduced force. That happens in pre-stressing strands in beams, and we call that relaxation. There's also another very familiar example of relaxation. How many of you have ever played a guitar? Okay. All right, you see where I'm going with this. So you play a guitar, after so often, you have to take those guitar strings and you have to tune them. Now, what does it mean, really, to tune strings? You're tightening them. You are increasing the force inside those strings. But the strings didn't get longer and shorter. The length of those strings is maintained constant between the mechanism at the end and the fretboard at the other end. So the length is constant, but the force inside them dissipates. That's why the note gets weaker, and you have to tighten it. That's called relaxation. The force dissipates under a constant length. It's almost the exact opposite of creep, but it happens. So I went off on a little bit of a tangent there, but material-related aspects, and it's also something you have to consider when you do pre-stressed design. In other words, if you've ever been to a pre-stressing plant, you know that what they do in pre-stressing is they apply a significant amount of pre-stress to a given steel element, let it go, and then that locks in a compressive force inside the beam. But from a design standpoint, you are not allowed to use that full amount of force that you got on day one to compute the strength capacity of that beam. You have to reduce it some. Like you're only allowed to use something, it can be like 85% or 82% or something like that. Because over time, there's a number of things that cause that force to dissipate. All right. So went off on a tangent, but at least it was relevant to concrete. Okay. So what I'm talking about here when I say a doubly reinforced beam is I'm talking about a beam that has not only tensile reinforcement, but compressive reinforcement as well. And I propose to you that really what we're going to have is two couples like we did with T-beams. We're going to have a regular old moment capacity couple from the tensile steel, but we're also going to have a couple generated by the compressive steel. Now, what gets challenging with doubly reinforced beams is determining whether or not the steel has yielded. Okay? So, real quick, let me show you a couple things. Maybe I should point something out here in terms of notation. For what we've done so far in this class, we've said that A sub S is the area of steel, right? Okay. What we're now going to do is refine that definition and say that A sub S is the term for tensile reinforcement. AS prime, compression reinforcement. D is the distance from the top of the beam to the tensile reinforcement. D prime from the top of the beam to compressive reinforcement. Does that make sense? Everybody okay with that? Okay. Now, let's go back to a fundamental mechanics question. Okay? How do you know if the steel has yielded? The strain has to be larger than what? Has to be larger than this, right? Has to be larger than the strain at yield. Now, we have never encountered a reinforced concrete beam in this class where the strain was less than the strain at yield for tensile reinforcement. Compressive reinforcement, that is very, very possible. Okay? So here I've got my strain profile. So it might have been a while since we've actually taken a direct look at this. So let's make sure we remember what's going on. So here's my strain profile. It's linear in nature. Okay? From the top of the beam to where the strain is 0, we call that distance C, right? Everybody okay with that? Now, to define this strain profile, we assume that the strain at the very top is 0.003. It's linear in nature, so we could compute this one as saying what, like 0.003, and it was D minus C over C. Now, how we did that was using similar triangles. We said that 0.003 is to this as this strain is to that, which that distance is D minus C, and we just solve for the strain. We're not looking at this strain, however, or I guess I should have pointed up and said we're looking at this. We're not looking at this strain. I want to know what the strain in this steel is. Okay? So watch this. 0.003 is to C as this strain is to C minus D prime. Okay? Does everybody see how I did that? Everybody good? Okay. So using similar triangles, I can now compute the strain in this steel. So this is the strain in the steel that's in compression. So epsilon sub S prime. And what we'll find is that there is a very real possibility that that is less than this. Okay? So let's walk through that. Okay? If the compression steel has yielded, okay, how do you determine the force in that steel? It is the area times Fy. Make sense? Okay. If it hasn't yielded, how do you determine the force? Well, it is the area times whatever the stress is. Okay? The stress isn't Fy. Okay? It's whatever the stress is. How do you calculate the stress? It's E times the strain. So for this stress, it's E times the strain. How do we calculate the strain? It's 0.003 C minus D prime over C. Everybody see that? Now, regardless of what, whether it's yielded or hasn't, we're still going to have to meet this equilibrium requirement that the sum of forces in compression have to equal the sum of forces in tension. So we're still going to use that regardless. But if it hasn't yielded, our equations get a little bit messier, okay? Because look at this. I propose to you that regardless of if it's yielded, the compressive force in the concrete plus the compressive force in that layer of steel up top has to equal the tensile force of the steel in the bottom. Okay? So how do we get the tensile force of the steel in the bottom? Well, that's just ASFY. No matter what, I'm still saying that I'm assuming this is yielded, and that will almost always be the case. Well, actually, it has to be the case. That's because we have that strain limit of 0.004. It's trying to enforce that that tensile steel has to yield. Now, how do we calculate the compressive force in the steel? AS times ES times our strain, which is what I got right here. Now, what about the compressive force in the concrete? It's 0.85 FC prime AB. What is A? A is beta 1 times C. Everybody see that? So do a little bit of rearranging, and it's funny how you get this quadratic equation. Y'all see that? Okay. So what sucks is if your compression steel has yielded, it's pretty easy to determine the capacity. If it hasn't, you actually have to solve a quadratic equation to figure out what this neutral axis depth is. Okay? So what we're going to do is two examples. We're going to do an example where the compression steel has yielded. I'll just go ahead and tell you. Then we're going to do one where the compression steel hasn't yielded. Okay? And then after that, that is about everything that I can teach you all for the flexural strength of reinforced concrete beams. After that, we're going to say, all right, this is flexural strength. We care about this moment diagram. But those of you who had me for structural analysis know that that ain't the whole story. There's also that. So how do we handle shear forces in concrete beams? And we handle them through the use of these stirrups. But I'm going to make reference to a number of things that I know my deformable students will love. Like, let's see, remember that? Oh, yeah. Remember that whole stress block? And remember Moore's circle? And we'll talk about some good stuff about how concrete beams behave in shear and what have you. All right, that's all I've got for you all. I'm going to go talk to IT. Sorry, hold on real quick. Okay, homework's due next Friday. No, the video, it's been recording. Yeah, no, it's been recording. So, so that's a non-issue. But all right, you all have a good weekend.